2:43. Okay, let's get started. So are we ready? Yes?
Yeah.
All right. Let's see.
Looking at time zones.
Why are we looking at I'm trying to figure out exactly when the recording starts. Because the podium seems to be about 3 minutes fast compared to my laptop, which... Uh-oh. Okay, never mind. Somewhere I have 100. Okay. Here we are, finally. Okay. Homework 3 is due tonight. I think 15 of you have already submitted. Lab 4 was posted last night. Its demo is due next Thursday, not tomorrow. And there's a pre-lab, which I think 2 of you have already submitted. Most importantly, there is a midterm on Friday. Midterm will be here, covering everything up to and including what's on homework 3, which includes the sequential timing diagrams and static timing analysis. Okay. Any questions? Yes.
Will there be questions on where you have to do Boolean algebra to simplify and you're not allowed to use a K-map?
Yes.
Fair enough.
Yes.
Are there any Verilog questions?
You need to know Verilog, very basic Verilog, yes. I'm not going to... If you've been doing the labs, the Verilog should be really easy. Any other questions? No other questions? Okay, I do want to, I know I've been helping a bunch of people. I do want to make sure everybody understands what an edge detector should be, because this is a fundamental component you'll want in future labs as well. So an edge detector only need 2 flip-flops. You do want this flip-flop here because otherwise you'll have some transients from the external input going up and down affecting Y. So you want both these flip-flops. And this first flip-flop actually serves the purpose of a synchronizer. So if you have a button feeding into this, you don't need to have a synchronizer in addition, because this is the only flip-flop that button connects to. If you do add another flip-flop in front of it, it won't hurt. It'll just delay it by another millisecond or so, or less. Okay. All right. Let's launch into today's topic. So in the previous lectures, we've looked at designing just little state machines. For actual lab projects, you're going to need a state machine, but you're not going, the whole thing is not going to be designed as one big state machine with a state diagram. You have components that do specific things, and you're going to need to organize your design with a state machine telling all these components what to do. And so we'll do a design like this. Probably a good time to look a little bit at Lab 4. So let's do that. In Lab 4, you're doing one of these designs. You're building a system, and there's a description, actually a video of what it does. Unfortunately, there are no speakers on the machines in the labs, and I just did want to point out there is audio with this, but you'll need to play it on a phone or a laptop or if you're in the lab, because the machines themselves don't have speakers. And you can see here's a suggested design of what it's going to look like. You're going to have a state machine, and then you're going to have some other components. These look familiar to you. And then these two are kind of new, and these are 5-bit counters, which you already have, right? Okay, and so the big thing, of course, is the state machine that's going to make all of these things do the right thing at the right time and cooperate. Okay. So let's talk about, let's do an example of that type of design. Here we go. Okay, so this is a this small example, trying to keep things simple, of the type of design you're going to need to do in Labs 4 and then again in Lab 5. Okay, in this example, we are building a bike counter for taps. The idea is very simple. We need to count how many bikes use the bike path every day. And this is going to be done by putting a sensor across the bike path. And when a bike passes through the sensor, it interrupts the signal. Light ray, usually, infrared, commonly. And so this is an electronic device, and it produces an output, high or low, and we will be connecting that to your circuit, which is in that box. I guess it's solar powered because I don't see any power here, but so this box takes as input just one wire with a high or low, and basically when the light ray across the path is broken, we know something is obstructing it. Now the question is, what is obstructing it? Because there are also other things on the bike path. Ground squirrels. Okay, so TAPS has done extensive studies with their sensor to identify what's a bike and what's not a bike. And they have decided, so they're the customer, so we're not going to argue with them, but they have decided that the signal you will see from a sensor looks like this when there's a bike. So they have a clock, and they will provide us the clock, and the signal from the sensor will be low, and then it'll go high for any number of clock cycles, and then it'll go low again. Okay, and if it goes high again within 16 clock edges, then it goes high and then low again, we will consider that a bike. Okay, so it won't be 2 unicycles because they can't be that close. Whether or not it's a squirrel jumping up and down on the sensor or in between the sensor, we don't know, but this is our spec. Okay. All right, so our job is to build that component which will take the input W and clock and detect whenever we see this pattern. W going high for any number of clocks, then low for at most 16 clocks, then going high again, any number of clocks, and then once it goes low, we will say that was a bike. Okay. All right, so this is what we're building. We're building a component with a clock and W as input, and as its output will be a 16-bit number indicating how many bikes we saw that day. Okay, all right. So let's see, what do we need in here? Let's see, our output is a number of bikes. what should we put in this big box here? Yes.
A pattern detector of some kind
Okay.
to fit something similar to an edge detector, but that detects two highs with a low of 16 or less cycles in between.
Okay. And what would we do with the output of that?
Increment number of bytes by 1.
Oh, okay. And what kind of device increments? A counter. Okay, so you want to have some signal which will go high whenever we see the pattern, and we will use that as, say, the increment or the count enable of a counter. Okay. All right, so we have one of those. Okay, so now I have to generate this signal that's going to go high for one clock cycle every time we see the pattern that looks like a bike. So in order to detect that pattern, what would I need to do? Do I need another counter? No? Yes, I think I'm going to need a state machine, but this is going to be an awfully big state machine if I have to have a state for each one of those clock cycles in between the two wheels. Yeah, but how do I tell? An edge detector will tell me when the first wheel hit, right? And then afterwards, I need to know that the wheel went low again, and then I need to count, right? Yes?
So, like a state machine hooked up to another counter?
Another counter? Okay.
Or kind of that counter serves as both an input and an output to the state machine?
Okay. All right. So the state machine is going to watch the wheel, but it's going to want to be able to count how many clock cycles occur between the two wheels, right? In order to do that, it's going to have its own private counter. We'll call this time counter. And this one only needs to count up to 15. So we can start at 0. It can just go all the way to 15. And basically, since we're going to reset it to 0 on the first clock edge and then count up. And so on the 16th clock edge, TC will go high. So that will be our signal. Hey, this is the last clock cycle if this is going to be a bike. Okay. And then, but I need to make sure this counter starts at 0. So I'm going to need to be able to tell it to start now. But I can just let it count. So this counter counts all the time, every clock edge. But when I need it to be 0, I can reset it to 0, so I can make sure that I start at 0 when I care about the count. Okay, all right. And so now we need our state machine. So we've pulled out the main components here that we need to do the job. There are different ways of doing this and hooking this up. We could have made a state machine in which we kept track of the number of zeros between the two wheels and used 16 different states to do it. That's probably not the best way to do it. That's like building a ring counter to count up to 16. That's a little overkill. And we know how to efficiently build counters. So instead, we're building a 4-bit counter to count up to 16. Okay. All right. So here's our state machine. Obviously, the state machine is going to take the wheel input from the sensor. And it has to tell the time counter when to start, right? And it's also responsible for telling the bike counter, hey, that was a bike increment. Okay. In order to do its job, it needs to know one more thing. Right now, this state machine just has W as an input. What other input does it need? It needs time up, yes. It needs to know when that counter hits 16, right? Because that's going to tell it whether that's a bike or not. So it needs the feedback from the time counter. When the time counter reaches 15, if you haven't seen the rear wheel yet, then that's not a bike. Okay. Something else here. Okay, so we're going to call these inputs a W and time up. You can name them something else, but generally it's easier to read your design if you use the same names throughout. If you need to instantiate a component more than once, then obviously you can't use the same names every time. But when you can. All right, so let's look at this now. So our state machine is supposed to detect this pattern, right? It has two inputs, W and time up. Okay, so let's design this state machine. What's the first state? Yes?
Is it chill?
No, this is an old slide. Sorry. Okay, I just mixed things up. This one's called idle. Okay, we could have called it chill. We could have called it Nefertiti. That's a little bit long, but all right. So we're sitting along here, minding our own business, and we have two inputs to pay attention to. Which one do I care about at this point? W. Okay, what should I do if W is 0? Nothing. Okay, doing nothing basically says stay the same. Don't react. Which means I probably want to do something if I see a W. So I'm going to want to change state if W is high, because obviously something happened, something hit the sensor. Don't know yet whether it's a bike or not. Okay, so we're going to another state. I'm going to call this one FW for front wheel. So we hope we don't know it's a bike yet, but let's assume that we're working on it. So this would be the front wheel if it were a bike, right? And so now we're in here. W went high. Okay, what should I do in front wheel?
Basically the opposite of idle. You stay in that state when W is high and leave when it's low.
Right. Okay, so now I'm processing ones, and I don't know how many ones there will be, but as long as W stays high, I'm dealing with the front wheel. When W goes low again, aha, the front wheel is over.
Reset time.
Yes. So now, this is when I want to reset that timer back to 0 on that clock edge, because now I want to start counting, because I need to keep track of how many clock edges there are before W goes high again. So I'm calling this one between wheels. Okay, so now we're between wheels. What if W goes high? Yes. No? What should I do? Yes.
If it happens within 16, then it's a bike.
Okay, so if I hit W while I'm still between wheels, I'm going to go to a state called rear wheel. Okay. Suppose I haven't hit 16 or 15 and W is still low.
And you stay.
Then I stay. Okay, so as long as time's not up and W is low, I'm going to just stay put. I'm still between the wheels. So if W is low and time is up, it's not a bike, right? In that case, I go back to idle. Okay, so while we're processing in here, as long as W is low and we haven't hit 15, we're going to stay here. As soon as W goes high, we're going to go here. But if W goes low and time is up, then it's not a wheel, and we go back. Okay. Now, one thing I want to pay attention here is there are 3 arcs leaving between wheel, and they are mutually exclusive, right? If W is high, we go here, regardless of time up. If W is low, then we either stay put or we go back to idle based on time up. So we have captured all 4 possibilities for the values of W and time up. Okay, and there's no overlap. Only one of these 3 arcs can be true, and one of them will always be true. Okay, all right. So rear wheel, what do I do in rear wheel? Yes.
Well, since you've already established that time is not up, it must be a full bike. So you output a 1 to the counter.
Okay, but what should I do in rear wheel as far as the next state?
If W is on, it stays the same, but if W goes low, then we return back to idle.
Okay, so I still want to process these 1s, right? If I go back to idle right away, then idle's going to think, oh, this is a front wheel. So I want to make sure that W goes low before I go back to idle. Right? If I were to go back to idle here, then on the next clock edge, I would think there's a front wheel. Now, and I'm going to actually increment the counter after W goes low. Now, you could decide to increment the counter here, but would it be okay to increment the counter here on this arc? No, because, yes?
Oh, because it would just continuously keep counting up.
Yeah, so while if W is high for multiple clock cycle and I'm incrementing it on this arc, or basically in this state, then that counter is going to count up multiple times, right? So we have 1, 2, 3, 4, 5. My counter would increment 5 times if I put the bike and signal in this state. So I definitely want it on an arc and definitely not on an arc that's looping. Did you have a question? Yes.
What if time's up and your wheel is high?
We go here. So if the wheel goes up right when time's up, that's still a bike. Okay?
That's precisely 16 clock cycles, and we're looking at less than
Then a recall.
16.
Right? If we were doing less than, then we'd want to break it the other way. Yes?
So the slash after RW, that's when W goes low, slash, that means you're sending an output to something
Yes.
that's not actually part of the state.
Right. So this is the notation where you have the condition and then the slash, the output you want on that arc. Right? Yeah.
Is there a reason why we output bike on the rear wheel to idle instead of the between to rear wheel edge, or is that sort of up to your design?
You could do it here. I mean, I guess if you were really picky, you could say if the bike rear wheel stopped there, you actually counted it before it had really passed. but I don't think that's going to be a big problem. But yes, if you were to count the bike on this arc, it would still be a bike, and presumably that rear wheel would eventually get through. And yeah, sometimes you have choices like that. Okay, any questions on this? Okay. All right, so this is, the major part of your design is coming up with the different components. For Lab 4, there's a suggestion of what there should be. For Lab 5, you'll be on your own. We won't give you a diagram. You can pick your own components. It won't be too different. And then for Lab 6, you're completely on your own. Okay. Yes.
But the time counter component, you output a 4-bit output. Where does that end up?
Nowhere.
You don't.
So I'm using this time counter, right?
Oh.
But I only care about when it's 15. I don't actually care what value it is in between. I only care whether it's 15 or not, right? So you can have components that you don't use the outputs of. That's perfectly fine. If you're not using any of the outputs, then you probably don't want to use that component then, or you shouldn't be using the component, right? But as long as you're using one of the outputs. One of the things Vivado does for you is it removes logic that you're not using. So for example, you have a nice 15-bit counter, and let's say you only want a 12-bit counter. Do you need to go and create a 12-bit counter? No. Use your 15-bit counter and just ignore the top 3 bits. Okay, Vivado will go and say, wait a minute, these flip-flops aren't going anywhere, and it'll go remove those flip-flops for you. And it'll go remove anything that's only going to those flip-flops, and remove anything else that's not needed. Now, the bad thing is, if you forget to hook up your outputs, say you don't put any outputs in your top level, your whole design will get removed. And I've seen that happen. Yes?
So in theory, you could have like a 100-bit counter for like each lab and just like save it for each one?
Yeah, okay, now it's doing some work to do this, right? And you probably think it's already slow. So you probably don't want to have a 100-bit counter to get down to 12, right? But theoretically, yes.
Okay.
Right, so it will remove logic. So if you have an output that you're not using, don't stick anything in that port. Just leave the port blank. Okay. If you have an input port and you don't want to use something, you need to be a little bit careful. Sometimes you can get away with leaving it blank, and sometimes you can't. I'll give you an example. If you're using your 15-bit counter and you don't want to load it, you never want to use the load feature, you need to set the load to 0. If you don't set the load input to 0, the simulator will give you unknowns, and then that's kind of useless. Okay? Vivado will likely put a 0 there for you, which is what you wanted, but it's not guaranteed. Okay? But once you set the load input to 0, the input bus, the D-in bus, that you can just leave unconnected because it's not going to affect your counter as long as the load is always 0. So we happen to know that making the D input a don't care is not a problem for the counter because the load is always 0. Okay? If you're worried about it, you can just always specify your inputs. Just set them to 0 or 1 according to what you want. Okay, all right. So let's see, where were we? We have our state machine. So the rest of this is pretty mechanical. So assuming this is correct, and one of the things that's going to happen in the lab is you're going to have an initial state machine, and then you're going to have version 2, and then version 3. So you're going to want this in your notebook, and you're going to probably make some adjustments as you go along. All right, but from this we can get our next state equations, right? We don't have to make a state transition table. We don't have to fill in K-maps. Instead, what we're going to do is write the values for each next state. So when am I going to idle? I'm going to idle if I'm already in idle and W bar, or if I'm in between wheel and I have W bar, not W, and time up. And I have the other way I'm getting here is if I'm in rear wheel and I have not W. So those are the 3 transitions into idle. right? Okay. What would front wheel look like? Yes.
Front wheel and W, or idle and W.
Exactly. Okay, so you can write equations that are true whenever the next state is a particular state. And for front wheel, the next state will be front wheel if you're in idle and you get W, or if you're in front wheel and you get W. Okay, so everybody understand how we're getting these? Speak now. Okay, I'll just put the other ones up for you. Okay. Now, what about the output? We have one output here, bike, and another one here. Bike needs to be true on this arc, right? So bike will be high when we are in rear wheel, and W is low. Okay, and reset timer will be high here when we are in front wheel, and W is low. Okay, so from this we would get the following. Ta-da. And this is just writing these logic equations as gate networks and plugging them into flip-flops. Why does this one have inverters? Yes?
So it starts on 1.
That's my start state, right. So remember, these guys are all going to wake up with 0 unless you do something. And here I've put inverters so that idle will be true, will be 1 when we wake up, because you need to be in a state when you wake up. Okay. All right. All right, so as usual, there's been a change. TAPS is a little bit worried about their definition of a bike. They say, we're not counting enough bikes, so would you please turn on an LED when something goes by and it's not a bike? We'd like some kind of signal, and keep it on until you see something else. All right, so you may be inclined to do this way, and I'm going to discourage this because this is really hard to do carefully. In fact, maybe I shouldn't do this at all. All right, so what not to do, even though this will work, is, well, I want to turn on an LED, so I'm going to need a flip-flop to hold the value of this LED. I'm going to call this error LED. And when do I want this LED to go on? I want it to go on basically when I follow the arc from between wheel back to idle, when what I saw was not a bike. Right? And so that's, let's see, one of these. So we are in between wheel. No, it's one of the arcs going into idle. So it's this one here, this gate here. When we don't have a wheel, time is up, and we are in between wheel. So I'm going to give that a name. I'm going to call that set error. And whenever set error is high, I want to make this flip-flop go high and turn on the error LED. And I'd like to keep it on, so I'm going to take the output of this flip-flop and feed it back in so that once this is high, it'll stay high. Oh, good question. So that's what that AND gate is for. That's to turn it off. So you know, if you do that, if you feed back this into an OR, you're going to have to find some way to turn it off, and so that's what we did. And reset error happens when you see a bike again, which is here. When you're in idle and you have a W. Okay. All right. Instead of doing that, you're much better off, because there are many, patching your circuit directly can cause other issues. You may cause something to happen when you want it to happen, but you may also affect the things that aren't happening. It's really difficult to make sure that you haven't affected anything else when you make a change like this. So instead of doing that, what we should have done is gone back to our state diagram and added a state. So this is the state that extra flip-flop, that error flip-flop is going to hold. And basically what we're doing here is instead of going back to idle, we created a new state called error, and we'll stay here. This is like idle. We'll stay here, put, until we get a W, and then we'll go to front wheel again. But in this state, we are going to turn on the output. Okay, so if we look at how this changed our circuit, you'll see that all it did was add an extra flip-flop, and the output of this flip-flop is the error, because we're only outputting it in this state. And we are going there when we are in between wheel, time is up, and we don't have a wheel, and we're here, and we still don't have a wheel. Okay, yes?
Is that triangle supposed to be an OT gate?
No. Okay, so you may see these things in here. These are just plain buffers, and in a real circuit, a buffer may have some reason for existence, electrical reason to exist. But in terms of logic, all of this, in terms of logic in your schematic, the purpose of a buffer is to allow you to change the name. So this net on this side is called ERR, and the net on this side is called error LED. In a schematic, you are not allowed to connect two nets that have different names. They're supposed to be separate. But this allows you to say, hey, this net is actually driven by this one. Okay? If there were a bubble here, then it would be inverted and it would be a knot. But it's not. This one is not inverted. In fact, the way you build buffers is to use two inverters. Okay, all right. So of course you're not going to be entering schematics, unfortunately. We used to do that in this class before 2017, is that students would enter their designs by putting blocks and connecting wires. And but now we have Verilog. So this is what you would do. But but it's important that you think about blocks in Verilog, because one of the things that happens is it looks like code, and you think of it as being executed and running and producing values. But really what running this code does is it creates that. It just makes flip-flops and gates and connects them all. And if we were to take everything here and jumble the order, change the order, you'd get the same circuit. Okay, the only thing you need to worry about in terms of order is that you declare the wires before you use them. But otherwise, we can, permute the lines in your modules and it won't change anything. Okay, all right, so I have a 20-bit counter here for the bike. And there's our 4-bit counter for the timer. I'm not using the load, so I just set it to 0, so I don't need the D in. I have 2 flip-flops. So I had a total of 5 states. So I'm initializing the 0 flip-flop to 1, which is why it's separate. And here I'm using a bus of flip-flops. So instead of having 5 lines of flip-flops, I only have 2. I have a separate line for flip-flop 0, and then I have a bus for flip-flops 1 through 4. And I need to feed it 4 clocks. I need to feed it 4 bits of 0 on the reset. I need to feed it 4 ones for the clock enable. And the input is the next state. bus, and the output is the present state bus. Okay. Now, where's the logic for the next state and the outputs? Well, I put that in a separate module. So this is the control logic. So let's go back a second. So we have this module which takes the wheel, time up, the present state, and the next state. And it produces the reset timer output, the bike output, and the error LED. Yes?
Why does your first flip-flop have a init B1?
Because what?
What does that do?
So this is a parameter that allows you to say this flip-flop should wake up with a 1 on a global reset. Right? If all my flip-flops wake up with 0, then all my flip-flops will remain 0, because my logic, if you look at the logic we created, right? Let's go back here. Every term here has a state. Right? These are all sum of products, and in each product term there's a state. So if all these state bits are 0, all of these will be 0. And it will never do anything. So you have to make sure you have at least 1, 1 if you're in 1 hot. Exactly 1, 1. Whatever state is your start state, it should wake up with a 1. Very important. All right, so we're back here. So these are two different styles. It's convenient to deal with your present state and your next state as buses, so that you don't have to write 5 lines of flip-flops. Now maybe you think 5 lines, that's not such a big deal. But later on it's going to be more than 5. And I always feel bad when I'm helping somebody and I see all these lines of flip-flops when one line would have done the same thing. And one of the things that happens is you need to change your code. And if you're changing something 16 times, it slows you down quite a bit. So I highly recommend that you use buses when you can. And buses of flip-flops rather than individual ones. Okay, so what we're doing here is we are giving names to the present state, and then the next states are providing the names for the next states. Okay, and so when I write my logic here, right, it looks exactly like the logic I had before, except of course instead of plus and star, I'm using the vertigo bar and the ampersand. Okay, and then here are my 3 outputs. You don't have to do this style. If this helps you reason about your logic, that's fine. This works just as well. Put a comment that reminds you which state this is, because you're going to have a hard time remembering what NS2 is. But you'll have no problem remembering between wheel, what that is. And when you read this, it'll make sense to you. Gee, I want to go to between wheel when I am in front wheel and I don't have a wheel and not time up, or if I'm in front wheel and I don't have a wheel. Okay, so that's one style. And if we then do the elaboration and look at the schematic, you'll see that it looks like this. The flip-flop, idle flip-flop is broken out. This is the bus of 4 flip-flops. This is the control logic because I put it in a separate module. And this is the bike counter and that. Now, you don't actually have to have separate logic. One thing that you might want to do is actually put the flip-flops here with your control logic. So there are various options of how to organize this. So now I've put the flip-flops inside the control state machine. If you do this, don't forget to provide the clock. This won't work without the clock. Okay. So let's talk a little bit more. Any questions on this? So you have, yes?
So for the second flip-flop on the right, I noticed that the clock is being multiplied by like 4, so I assume there's like 4 bits of the clock.
Yeah.
Could you just really quick explain that?
Okay, so this is a bus of flip-flops. It's not one flip-flop, it's 4 flip-flops. Each of these inputs needs a bus then of width 4. Okay, they're all getting the same clock, so I just have to replicate the clock 4 times. I don't want to reset them, so I need a bus of 4 zeros. And I do want them to load on every clock edge, so I need a bus of 4 ones. Now the next state and the present state are already buses. Of course, I'm leaving 0 out, so I have to actually put the index 4 to 1. If I were to use the entire bus, I could just say NSPS. But because I want to leave 0 out, I have to indicate that.
That makes sense. My only question is there a reason you're using 4 individual clock, like the clock replicated 4 times, rather than just inputting 1 clock and using it for each flip?
Well, so I'm being careful here. There is some convention that if there's a single one that it'll replicate it for you, but I've seen it not do it. So this is absolutely safe. I mean, you may get away by just putting the clock once.
That makes sense, thank you.
Of course, this one is separate because I need this one initialized to 1. Right? If you have a register and you don't care, they're all initialized to 0, you can just have 1 bus of flip-flops. Right? In fact, if you were making a 16-bit register, it could just look like this, 1 line. Right? This is a 16-bit register. Its input is the bus D. Its output is the bus Q. It has 16 loads. We're not doing any resets, so the resets are set to 0, and 16 clocks. Okay, that's a lot better than that, right? Don't do this. Okay, what about a shift register? How would I do a shift register? Well, I can do the same thing. I'm going to have a bus of 16 flip-flops. 16 clocks, 16 zeros, 16. Now I need an input. I'm going to use the clock enable to tell these guys to shift, right? So my shift input is going to be replicated 16 times since I want them all to shift simultaneously. Now, what do they shift in? Well, so the output is Q. The output of the shift register, what's being held by each one of these flip-flop, is called Q. And so if I'm shifting right, is that right? Okay. So I'm going to lose Q0, right? Q0 is going to disappear. And so what I need to do is take Q15 through Q1, and that's going to move over. And then I need a new bit here, so that's the in. So I form a new bit which loses Q0 and has in on the left. And that's what gets loaded into the flip-flops. So this is how you would do a shift register that shifts right. Okay, if you wanted to shift left, what would you do? Yes. I would do 0 to 14, and I'd have in over here, right? I'd have to put the in on the other side, right? Okay, or that, or I'd take the mirror image of the slide. Okay, no. Okay, all right. What about our ring counter? Is this a good 6? I'm here while I'm doing is instead of before I had in here, and what I'm doing here is now I'm connecting Q0 to in. So this is my ring counter, right? No? What's wrong?
They're all going to initialize to 0.
Oh, darn. Okay, yeah. So little problem here is all of these flip-flops are going to wake up with zeros, and that makes for a very dull ring counter, right? So I have to make one of them wake up with a 1, and so it gets a little tricky. How do I do this? Well, so there are 2 different ways that I can think of doing this. Here's one way. Pull out one of the flip-flops and deal with it differently. So initialize it to 1. And that means I can't have it as part of the bus. So now I deal with the rest of them as a separate bus. Right? So all right, so the input now is, the input to these guys are 15 through 1, and then the outputs are 14 through 0, and then this one gets 0 as an input and outputs 15. So I can do it that way. Here's another way. I could use the 2 inverters. If I do it this way, what I'm going to do is I'm going to name the outputs of the flip-flops QF. So I have 2 buses now, Q and QF. The outputs, the actual outputs of the flip-flop are called QF. Okay. Now, for all of the flip-flops except the first one, the output Q, the final output Q, is the same as QF. But for the first one, it's actually the negation of the value that's held by the flip-flop. So here, this NOT gate happens here. Okay, so what gets loaded back in here? Well, I need to negate Q0, so this is where this inverter happens. And then the rest of them are just shifted as before. So I take Q15 through Q1. So this is another way of doing your ring counter. Okay. Any questions? Yes?
Is there like a preference between the 2? Does it matter?
As long as it works. But please don't do this. I know this is what you're, excuse me. I know this is there's a tendency to stick with what you know works. You're comfortable with it. This can cause, this will slow you down in future labs. So it's really important to be able to master using buses here. Okay, and let's say you decide that you want to change this, and you have to go edit every single line, and you make a typo, which is the chances of making a typo increase with the number of lines you're editing, right? Use a small d instead of a capital D. Have 2 6s instead of 6 7. Okay, it takes a heck of a lot of time to track down these errors. It's better to make major errors than minor little picky errors that are hard to find. Okay. All right, so I don't have anything else today. Any questions? You all ready for the midterm? Everybody look at the sample midterm? No? Yes?
Definitely didn't have a midterm for a different class today.
You did? Okay, that's nice. You don't have any other classes, right? No? Okay. Any questions on anything? Let's see, what do I have here? You do know that there is a sample midterm, right?
Yes.
Right? And you do know that all the slides are here. And you do know that all the homework solutions, except of course solution 3, are there. Solution 3 will be there tomorrow. Yes?
When you, this is kind of a conceptual question. But
Sure.
when you're doing a SOP key map
Yeah.
and you have don't cares, do you circle the don't cares too, or is it just the zeros?
So you mean when you do the product of sums?
Yes, probably so.
And so when you do the product of sums, you are basically just swapping ones and zeros. So again, you would cover the zeros and the don't cares. So again, you treat the don't cares as ones too.
They're wild cards.
Right?
They help you.
Any other questions? No? All right, I will see you Friday then.